So,
exactly.
Yeah, very good connection.
So we are going to the second part of this seminar series, which is the part where we have the flash talks. Just very briefly, we had this idea of introducing shorter talks where we're going to have 3 people. They're going to have a 10-minute presentation, each of them. And they're going to go one after the other. So we will wait at the end of the 3 flash talks to then ask questions in the same format that we have just done with Luca. So both the chat on YouTube and on Zoom. So the 3 speakers in the order that we have are Nick Garabedian from KIT. He's a Humboldt postdoctoral fellow and a group leader. His title is Big Open Data in Tribology, Big Open Data in Experimental Science. So perfect link to what I was asking as well. He will be followed by a colleague of his, which is Ilia Bagov from KIT as well. He will talk about give tribological data a meaning, VocPopuli and PIDs. And finally, we have Ebru Cihan from TU Dresden. She's a postdoctoral research fellow, and she's going to talk about fingerprint of a structural phase transition during superlubric sliding. So as I said, let's go one after the other. So once Nick has finished, we will just continue. Please, Nick, you can go.
And sorry to interrupt quickly. Because we have started late, we have decided to skip the break that was initially scheduled for after the flash talks Q&A. So there will be, after the 3 talks finish, 15 minutes time to ask questions and give answers. But the 15 minutes break that should have been after that will be cancelled. So we only are 15 minutes late and not 30. And again, my sincere apologies for these problems with the audio in the beginning. So then, Nick, stage is yours. Thank you.
Thank you very much, Martina and Michael. I hope everybody's seeing my screen. Yes, I see the thumbs up, Martina. Thank you. Thanks for the introduction. And yes, my name is Nick, and I'm currently a group leader of linked tribological data at the Karlsruhe Institute of Technology. My background is in experimental nanotribology. That's my PhD. And since then, I've taken sort of a pivot towards data and big data. So we all know that investments in science have brought us unimaginable, exponentially growing economic prosperity. However, the way to conduct science also has to evolve and improve over time. So our journey to start dealing with big open data took us to the point where it came from the desire to find a united solution to some of the existing and future challenges that we face. So the story goes the following way. We were, for some time, we were wondering how can we become a next generation research lab. And we defined a few metrics through which we could achieve that. And one of them was we wanted to preserve our data better. We wanted to accelerate the lab operations, just in general, from a managerial standpoint. We wanted to be able to share our data more efficiently within the lab and outside of the lab. And finally, we wanted to enable our data for machine learning. Now, because big data has 1,000 definitions probably, a more specific and somewhat actionable goal for us became FAIR data. And to those of you that are hearing this for the first time, FAIR data is an acronym of findability, accessibility, interoperability, and reusability, which are a set of principles and guidelines to observe when dealing with data. And the overall outcome of using these is that communication with other researchers becomes easier. The information and the data that is provided in a fair manner becomes machine actionable. And last but not least, something that I see often, not mentioned often enough, I think, is the fact that once data is organized better and it's findable, more findable, then the need for repeating already performed experiments goes down. Thus, we avoid wasting very valuable scientific resources. So with these things in mind, what we did about a year and a half ago was to do a proof of concept where we conducted somewhat standard showcase experiment of lubricated contact of metal against metal contact. And we basically asked the questions, can we do this experiment fairly? And what is fair for tribology? The results of all this are summarized in 2 publications that came out this year, and the data is openly accessible with the metadata accompanying it, with an ontology that connects the data inside and the metadata, and this is freely available. You can find this in the publications. However, without going much deeper into the publication and all the work it took to define 3,000 terms or so at some point, the major outcome of all this was that we realized that it's a known fact in tribology that a lot of the most of the tribological performance of materials comes from the surface preparation. So really big data in tribology is becoming big data of sample preparation or so. Of course, the experiment has to be accounted for, but the sample preparation and all the different types of processes becomes really central to the whole problem. So with this knowledge in mind, we shifted towards asking ourselves, how can we make fair data a daily way of conducting science in the lab? So the new framework that we operate under looks like this. That is probably a little crowded, so I will actually run this through a few stories. So the first story is about a PI who wants to make their data open, given some governmental or funding requirements or self-motivation. Now, maybe this PI will go to an electronic lab notebook provider to help with that. And there are many solutions for electronic lab notebooks. Many of them work really well, and they're great for organizing the results of scientific work. Now, having your data in an electronic lab notebook, it makes it very easy to share to an open repository. However, the problem here is that electronic lab notebooks organize the results, and it is somewhat challenging to give richer meaning to the inputs to the electronic lab notebook. And here's where our VocPopuli solution comes in. This is going to be described in the next flash talk, but basically this is a controlled vocabulary management tool which enables the creation, curation, management of metadata, the pieces of data that describe the data. And this is what, to us, opens the door for big data and really scalable machine learning. So the vocabularies in VocPopuli can feed into the electronic lab notebooks, which then can make the data open. And this yellow arrow over there is where I believe we can make the data truly fair, as it is a requirement by the FAIR principles to have fair vocabularies associated with the data. In the next story, well, I have a quick preview of what VocPopuli looks like, but it is a glossary of terms. Here you see for a block specimen that you can hierarchically describe it with its general information like location, operators in charge, and so on and so on. There are hundreds of these descriptors which we assemble through the process that is part of VocPopuli. Now, another user story here would be a curious student, newcomer to the lab, who wants to do machine learning on the data. Well, here they would need something like an ontology. And for this, we have the solution called On2FAIR-Cook, which it is in its early development right now. But essentially, it enables the metadata to be fully connected before it goes in the electronic lab notebook, and thus enables machine learning. I need to say that these two are currently part of a project called MetaCook, which is funded by the Helmholtz Metadata Collaboration. And we have collaborators from 3 more labs sitting in another institute in the north of Germany called Hirion. So we are testing our solutions as we're developing them. The Another user story now would be of another student who is, say, in the early stages of their bachelor's degree, who would like to learn about the lab's operations. So with this, here again, we can think about the vocabularies that were developed in VocPopuli as a place where newcomers to the lab can find a description of the procedures that take place in a lab and thus become an easy entry point to any new student. So the vocabulary is really, once a scientific group gets together and puts their thoughts into organizing what they talk about on a daily basis in a structured manner, it's a game changer for the entire operations of the lab, and it makes things more efficient. The last point on this slide would be the so-called fair-safe package of solutions, which we're also developing. These also feed from the vocabularies, and they basically make the whole process reliable by integrating with, say, the manual process in a tribology lab, like polishing a sample. Now having a vocabulary makes it very easy to construct an application called FS Digital Book, where you can make everything on the front panel of a tablet so that it's easy to use next to your grinding or polishing machine. You can also, using these schemas from VocPopuli, you can use a validator to make sure that the data that is stored in the results management systems of any of the electronic lab notebooks is within the schema that is prescribed before publishing it in an open way. And there are other solutions as well which interact with the regular work of experimental scientists. And just to reiterate, once again, we believe that everything starts at VocPopuli or similar solutions for metadata management. And we are not trying to replace electronic lab notebooks. I think they are doing a great job, but actually we're trying to help the adoption of electronic lab notebooks by making it easier for users to become digitalized. And the results, basically, it takes, at this point, takes about 2 minutes from the results, for the results from the tribometer to be uploaded to our ELN so that I can see them on my phone anywhere in the world. And it makes it easy to trace back accidents and correct for them because all the metadata is stored automatically. This all took us about 2 years to set up. Now, we've done the heavy lifting. I would say that with the outputs, it can take from hours to months, depending on the goals, to set up in another lab. So was this all worth it? I would say yes, absolutely. Thank you very much for your attention, and I'll be looking forward to your questions after my talk, or after the next 2 talks.
Thank you, Nick. We can go on to Ilia's talk. And also, yes, applause.
Sure. Thank you, everyone. Let me just share my screen with you. I hope, meanwhile, that the audio is okay. You can see me. That seems to be the case. Cool. Well, obviously, this talk is going to build upon quite a lot of what Nick just showed us. But before I start, just a quick introduction on my end. So I'm Ilia. I work in Nick's group at the KIT, the Karlsruhe Institute of Technology, and I am tasked with leading the software development of the tools which he just mentioned. Now, this presentation will dive a bit more in the technical side of the previous one, when here I will focus mainly on VocPopuli, which is, so to speak, the central part of our framework. Now, we use VocPopuli to basically answer the question, how do we teach a computer to think? Or in a more technical manner, how do we generate fair machine-readable data and metadata with the help of controlled vocabularies? Now, before I dive into VocPopuli itself, I first wanted to start with 2 simple definitions. The first one being that of controlled vocabularies, or at least the way which we see them in our group. Now, controlled vocabularies are basically lists of terms. These terms can have hierarchical relationships with one another, and they also have definitions, as well as some additional information, like, for example, synonyms, data types, if those terms are later to be converted into ELN records, and so on. Controlled vocabularies are used to define and describe the relations between entities in a given domain. However, this is done in a fairly basic and simple manner, I would say, which isn't necessarily bad. A more detailed description of a given domain can be achieved with the help of ontologies. Now, ontologies also describe the relations between entities in a domain. However, these relations aren't limited to hierarchical ones. They can be as richly defined as the user or the developer of the ontology wants to. The tools which we use to work and develop, controlled vocabularies and ontologies are VocPopuli on one hand and ontfercook on the other one. Now, the interesting point and thing is that controlled vocabularies can actually be converted into ontologies in a semi-supervised fashion, but the prerequisite for this is that the vocabularies themselves have been developed according to some best practices in the domain. Now, moving on, and maybe just again as a quick overview, this is the Karlsruhe lab framework. This presentation will focus on VocPopuli, and yeah, that's all I want to say here. Now, what I will show you next is just a small video demonstration of some of the basic use cases, features, and so on of VocPopuli. This here would be the first screen which a person would see. Now, you can see here that it says login with GitLab, and the reason for this is that that VocPopuli is basically, and speaking in a very basic fashion, a front end for GitLab. So all of the vocabulary development which happens with the help of VocPopuli is also mirrored in the background in GitLab, and in the form of different GitLab repositories. Basically, we have one repository set up for each of the vocabularies which people can develop with VocPopuli. The first step when logging in to the tool is to choose a vocabulary which one would like to edit. In this case, this is the cup grinding vocabulary. Now, I won't go into details about the semantics of each of the terms here, but you can see that they are structured in a hierarchical fashion. Each one of the terms has a data type associated with it. The reason for this is that these terms can be looked at as metadata fields, which can later on be exported into electronic lab notebooks. And yeah, here you can see a different data types. So we have dictionaries, strings, individuals, and so on. Now, a very basic use case, I would say, is that of adding new terms to the vocabulary. This can be done fairly simply. For example, using the Add New Child Term button, which opens up this form. Now here, I wanted to add the term student trainee to the vocabulary. Student trainee is just a kind of user role. As soon as I clicked on Add New Child Term, this form came up. And here you can see the different kinds of information which one can input for a given term. So the first one is the term name itself. Afterwards, you can choose an individual, a data type, which in this case would be individual. Following this, a person can input the definition of the term. And this is actually a required element, so a person must input the definition. And then the additional fields which you see here are, for example, synonyms and translations. And also basically the different ways in which the newly defined term can be related to the terms which are already present in the vocabulary. So, for example, here on the left side, you can add relatively broader terms to the one which is being defined. That is to say, those terms chosen here are the ones to which the newly defined term is a subterm of. Now, that's a lot of terms there, but that's basically the gist of it. And we also have so-called related terms, which are related to the one being defined, but not in a hierarchical fashion. Now, as soon as the term has been submitted, it's shown here in the vocabulary, but please keep in mind that its status is not approved, which means that the term itself has not been officially approved, officially approved by the vocabulary moderators to be used in the vocabulary. Now, if I click on it, I get this view here, which shows some of the more detailed information about the term. Information such as its definition, its data type, its broader terms, and these two IDs, the global ID and the local ID, which I'll describe in a bit more detail later on. Additionally, I can also comment on the term, basically facilitate a discussion about it. And afterwards, I can also edit it. So here I'm adding a German translation to its definition and submitting it to the vocabulary. And this is the result. So you can see that the translation is shown there. Additionally, people can also add images to terms. So for example, here I'm adding an image of a cup grinding machine to the cup grinding machine term, just to make it a bit more not only machine readable, but also human readable. Now, following this short demonstration of VocPopuli's features, I would like to move on to some of the details about what happens under the hood when a person uses VocPopuli. Now, as I mentioned in the beginning, VocPopuli is strongly based on GitLab. Right now, I want to show you what happens in GitLab when, for example, a person wants to define a new term, and let's say that that term is the term pen in the cup grinding vocabulary. Now, as soon as one initiates the term definition process, a new branch gets created in the repository which contains the vocabulary's terms. All edits done to that term are basically they get stored in that newly created branch. Then after some time, that term can get approved, which means that the version of the term which got approved gets merged to the main branch of the repository on GitLab, after which people can basically add new terms to the vocabulary. Now, these processes are defined, sequenced, and identified using 5 IDs. I'm seeing right now that I'm a bit short on time, so I won't go into too much detail about them, but these IDs define the states of the vocabulary itself, as well as the terms themselves at each given point in time and after each edit to the vocabulary. Now, moving on to some more VocPopuli's features, which, as I said, are strongly dependent on GitLab. VocPopuli offers, first of all, Git-based tracking, meaning who did what at which point in time. This is strongly connected to basically establishing a provenance of the vocabulary itself. And related to that point is also the possibility to annotate the generated repository as well as its provenance with the prof data model, so the prof DM data model. And additionally, we're also able to, we're not able to, the vocabularies themselves are stored as SCOS ontologies, which is a standard for thesauri and vocabularies, which facilitates the conversion of the vocabularies into ontologies. And that's just one of its benefits. Just as a final point, a summary to my talk today, and mostly to VocPopuli. Now, VocPopuli, as I said in the beginning, is a tool for collaborative vocabulary management and development, not only of vocabularies, but of fair vocabularies. It serves as the entry point to digitalization, meaning that it can serve as the entry point to laboratories who want to digitalize their data with the help of electronic lab notebooks, for example. And it is also a step towards scalable machine learning. Last and definitely not least, these are all of the people who take part in the development of the Karlsruhe lab framework. And that's everything on my end. Thank you everyone for the attention. Sorry for taking a bit more of your time, and I'm looking forward to the questions.
Okay, thank you very much. Ebru, you're up. Thanks. We are a little bit short, but that's fine. So thank you all.
Okay, I guess now I can start. Great. Okay, after the beautiful fair data presentations, I will turn the topic to nanoscale superlubricity and be more experimental. But first, let me quickly introduce myself. My name is Ebru Cihan, and I'm currently a postdoc at the Technical University of Dresden. But in the context of WeSST today, I would like to talk about the results of my previous work on the effect of direct phase transition on superlubric sliding. So let's get started. Nanoscale superlubricity is just one of the amazing phenomena discovered using atomic force microscopy in friction measurements. It is characterized by the ultra-low friction observed between atomically flat and incommensurate surfaces through collective force cancellations without wear and plastic deformation during relative motion. Theoretically, if the two flat contact surfaces are incommensurate, there will be no interlocking state between the atoms, and as a result, the atoms will slide easily over each other, resulting in very frictional forces. And we can explain it in this way. As the contact area and thus the number of atoms in contact, or the sliding interface increases, the potential energy barrier per atom will decrease, and the atoms will manage to stay at a higher level of the energy barrier. And this naturally means that sliding of atoms becomes easier. At this point, it is very important to systematically analyze this phenomenon of superlubricity, and for this analysis, we can or we need absolutely well-defined contact areas. So an alternative tool for this purpose would be to use nanoparticles with well-defined contact areas, which we can manipulate using an atomic force microscope tip on a flat substrate. Because then this will allow us to analyze sliding friction as a function of contact area or number of atoms at the sliding interface with a scaling factor of gamma. So for well-ordered crystalline nanoparticles, this scaling factor gamma is calculated between 0 and 0.5, depending on the shape of the particle or the level of the commensurability between the surfaces. For randomly ordered amorphous nanoparticles, this gamma should be well-defined as 0.5. And this clearly indicates that less effective superlubricity is expected for amorphous structures. Previous experiments with crystalline gold and amorphous antimony nanoparticles confirmed this theory very well. That is, a different efficiency is demonstrated for crystalline gold nanoparticles where lower friction is achieved. This result is actually good, very good, but not sufficient. For an atomic-based explanation of superlubricity, because it has been demonstrated only for different type of materials. In other words, we still have an open question regarding the chemical nature of the interface, and that question also needs to be answered. So this question will be the starting point of this work. Namely, to investigate the atomic origin of superlubricity, we also need to analyze the same material in two different phases. And of course, we can achieve this through a direct transition from one structural phase to another by heating, for example. For this, we chose antimony nanoparticles because from our previous experiments, we know that we obtain amorphous antimony nanoparticles as a result of thermal deposition in our ultra-high vacuum chamber. And we also know that it is theoretically possible to convert the amorphous antimony to crystalline antimony by heating. So for this purpose, we first produce our antimony nanoparticles in our ultra-high vacuum chamber by thermal deposition, and then we transfer the sample to the atomic force microscope without breaking the vacuum for further manipulation experiments. As you see the antimony nanoparticles on graphite here, this is a general overview of the antimony nanoparticles after deposition on graphite. For further manipulation experiments, we transfer the sample, as I said before, to atomic force microscope. And then the nanoparticles were laterally manipulated on graphite at different temperatures between 300 Kelvin and 750 Kelvin. So all nanomanipulation experiments were performed as a three-step process. To avoid scattering induced movement of nanoparticles, the sample was first imaged in non-contact mode, and then a nanoparticle suitable for manipulation was chosen. Then the AFM tip was placed directly next to the nanoparticle, and the system was switched to contact mode, and then nanoparticle manipulation was performed laterally. After the manipulation, particle displacement was confirmed again in non-contact mode. So here's an experimental data where these are the AFM images showing nanoparticles, the location of nanoparticles before and after the manipulation. And here is the tip, and here is these AFM images. And then this is show the lateral, the friction signals during manipulation. AFM tip gets in contact with the nanoparticle first 150 nanometer, where we also see a sudden increase in lateral force signal, which is the static friction peak. And then immediately after that, the particle begins to slide, which is the sliding friction. So this process was first applied for 3 nanoparticles, and the following results were obtained. And the following results were obtained, and accordingly, we can talk about 3 different regions for the specified temperature range. First, friction decreases with increasing temperature, and then this decrease continues, and this decrease continues for a while, and then at even higher temperatures, it increases slightly, as shown in the yellow area here. And additionally, the gray background color shows here a typical phase transition temperature of nanoscale antimony, and the continuous lines marked in red and blue were calculated according to the thermally activated stick slip, thermally activated Bront-Holmeston model, and they reflect different energy values for low and high temperature region. Due to time constraints, I will not go into further details at this time. So then, interestingly, this friction reduction remained constant here after the sample was cooled back to room temperature. We can see it easily with this red data points, and this made us think that there must be a reversible phase change in antimony. So to further analyze this, we performed additional manipulation experiments and manipulation experiments on a freshly prepared sample, and antimony nanoparticles were first manipulated at room temperature, and then at 500 Kelvin, and finally again at room temperature. As a result, these experiments confirmed previous observations. As you can see, friction is reduced by a factor of log2 when heats to 500 Kelvin, and this friction change is then found to be reversible since the same level of friction is measured after cooling back to room temperature. So before I finish, let me quickly relate this friction change to the scaling of superlubricity. If we fit the data we obtained at room temperature before any heat treatment with a fixed scaling factor of 0.5, we can achieve a reduced scaling factor of 0.42 for the data we obtained at room temperature after heating. And this can be attributed to the increased efficiency of force cancellations at the sliding interface, which becomes more regular due to the amorphous crystalline phase transition in antimony. So with this, I'm come to an end. In summary, we try to show the effect of direct phase transition on superlubric friction. The last but not the least, these results highlight the importance of atomic structure at the sliding interface in the superlubric regime. With that, I would like to thank you for your attention.
Fantastic. Thank you, Ebru, and thank you for all of the speakers in this Flash Talks session. Round of applause. Sorry, let me do this. There you go. So now we have about 10-12 minutes for questions. Please feel free to ask questions about any of the talks we just had, both the speakers in the Zoom chat and if we have question in the main chat on YouTube. Yes. Is anybody on already?
So far, no questions on the main chat.
Okay, go on.
As I can see, but I have questions. Actually, to all three, and I will just ask three in a row. Like I'm giving very short Flash talks, and then you can answer in a row, I guess. So first for Nick. So how you mentioned it's dependent on the use case, of course, to implement this in a lab. But I'm curious about like the interest you have gathered so far. I mean, I know this is very new and the publications are new, but this seems to be extremely useful, I guess. But then I have, in my experience, not all people are, very willing to share data immediately. So this is also something I didn't get maybe. So you can do this locally, I guess, and then share as much of the results as you want, or will this be uploaded immediately and accessible to everyone immediately? Then my question for Ilia would be about the similar thing, of course, with this Git-based approach. If this is done, let's say, in a repository for each user separately, and then what happens if there are large conflicts? And for Ebru, something I didn't quite get, when you in these colored lines you showed with the different regimes of the friction, these you said were fits to the data, or these were separate calculations based on the thermal activated PT model? And if that was separate calculations, which how did you choose the potential for that? Okay.
Let's start from Nick. Otherwise, it's going to be like a concerted answer.
Yeah, so that's why I wanted to make the distinction between open and fair data early. Fair does not mean open. Now it's the researcher's choice to make it open. Often it's not if they get funded from public sources, because I think it's only the ethical thing that if you're playing with taxpayers' money to give back to society and share your outputs, that's actually the ethical thing to do. And there is going to be a cultural change in that respect, and people's fears will probably be overcome. But as of right now, there are so many applications of fair data that don't just include open data. So I would say that that's just part of the story, the open part. And speaking about adoption, I have gotten pretty good feedback. It's usually the people that find us are the ones that are already conditioned to look for something related to data, and they've gone through the thought process of what is the significance of data. So when they come to us, they're already aware of the fact that they might need to do some of their data open.
Thank you.
Yes, moving on to me then. I hope I remember your question exactly, Michael, but basically, I don't think I had enough time to describe that in detail, but the way we go about defining these repositories and working with them is that each vocabulary, which is to say each research group, more or less, is given one repository in which they define their vocabulary. So all of the members of that vocabulary definition team, so to speak, are also members of that repository in GitLab. Now, the way we prevent merge conflicts is more or less the following. So I showed that picture, that slide with different branches for each for the development of each of the individual terms. All of the development done on the vocabulary is done in these individual branches, and it is done in a way which, so the workflow itself is programmed in a way in which merge conflicts aren't really possible. So on one hand, we only edit these branches. The main branches themselves, the main branch itself stays constant, and it contains the terms which have been approved in the vocabulary. Additionally, these edits aren't done in a single file, but rather we generate different files for each version of each term in its development branch. And these two parts basically allow us to define and develop vocabularies in terms without worrying for merge conflicts, because the how should I put it, the most severe issue which could arise is that two people submit a terms definition at exactly the same time. So literally at exactly the same point in time. But even then, this would only lead to two files being generated in the branch, in the development branch of that term, which again doesn't really lead to merge conflicts. So yeah, that's the technical explanation. I hope it managed to answer your question.
Thank you.
Yeah.
Cool, thanks. Ebru, do you remember the question, or Michael, you want to do it again?
Actually, I couldn't hear Michael very well. Or I would be happy if he can repeat. And a bit loudly, maybe, sorry.
Okay, so my question was, the colored lines you showed, they looked like fit to the data in the different temperature regimes. So for the crystalline and non-crystalline.
Okay, the last presentation, okay, slide maybe you mean. Okay, yeah.
So those were, I didn't see if those were like fits, like just, you know, trend lines, or if you mentioned something about thermally activated Prandtl-Tomlinson model. So I wanted to know if these were calculated lines, and then how do you get the potential for this model?
Okay, I see. Okay, I understand your question. Thank you for the question. First, actually, I said fit. You're right, but they are exactly calculated lines. I mean, we first calculate depending on, you know, the energy barrier E0 value of each particle. I mean, each, let's say, antimony. We first calculated gamma scaling factor, and then we use this number to, I mean, to make these lines as a fit on the graph. They are calculated values, yeah.
Okay, thank you, thank
you. We probably have maybe 4 minutes for another question. We don't have any question in the chat. I do have a curiosity, a technical curiosity about creating this metadata or establishing the metadata, but thanks to the question from Mikael, actually I understood a little bit more. I'm curious about things like for experimental data, so for metadata associated to experimental approaches of various types, you also do define, I don't know, units, error bars, all of these things. Is there a unified way to do so? Like, for instance, you insert the value and then there's an automatic way of unifying the units, so it's all self-determined, self-imposed.
Maybe I can take this. So I would say it's both. It's up to the users. In our case, we did define our units, and units are tricky, especially in tribology. I mean,
yeah,
we don't have units like a named unit for wear, for example, or wear rate. So you have to be very careful with units. But the strength of ontologies is the fact that you can relate what you mean to some other definition. And we have this in VocPopuli as well in vocabularies when you put a synonym. So if I call, if I use the German word for friction, you can put that as a translation and it immediately relates to that. And if somebody has defined it in the other language, that definition from the other language gets carried over in your definition automatically. So that's really the strength of big data and linked data. And
Okay.
the point is that you just have to put it semi in the right way in which we try to guide the user to put it in, so that the data finds its place automatically.
Okay, I see. Okay. There's one 1 minute for one question. What is the question?
So
And
question is
to
in
whom
the
is
chat
it?
from Research Space. Question for Nick and Ilia. Very quick answer, please. To what extent are the controlled vocabulary and ontology frameworks you have created tribology specific? And to what extent are they generalizable universal?
I usually say that if you manage to digitalize tribology, you're fine on all other sciences. So they are general.
Yeah, I concur. Very general. So yeah.
Okay, that was quick. Well, thank you very much for all of the speakers to help us out to be in time because of these initial technical problems. We were a little bit off. So thank you very much. I think